In this set of notes, we're going to relate what we learned in the previous note set about matrix algebra to how this applies to simple linear regression. So recall that our data is going to consist of n paired observations of the predictor variable x and the response variable y. And so further, recall that we're going to use the data to fit the simple linear regression model. And so notice here I do have the model. And if we have n observations, one way to think of this is we could put subscripts on the model and write it out n different times. So for example, here we have the model applied to the first subject all the way down to the nth subject down here. And so you'll notice that the intercept and the slope do not change from person to person, but what does change from person to person is what we observe for the explanatory, as well as the random error, and then finally the response. And so again, we're writing this as the matrix, or pardon me, as the model. And so notice we could represent this as three different matrices. We could view our response variables in a column vector. Also notice this one will be a column vector as well. And then finally our error terms. And so we have these three matrices here. So as stated earlier, notice we could express the response variable as a column vector, and notice it will be an n by 1 column vector, or we could look at the transpose. We could do the same thing with the error terms, which again will be an n by 1. And then finally we have the matrix here. Notice since these terms are added, this is also an n by 1 matrix. Now it ends up that this particular matrix here that has the slope and the intercept, it can actually be viewed as a product of matrices containing the response variable and a matrix of the parameters. And so this is how we could find it. So first, we're going to start out by looking at this n by 2 matrix. So this n by 2 matrix might look a little bit funny to start out with, because notice we have a column of ones here, and you might ask, well, where is that column of ones coming from? Well, it ends up that we need this column of ones because when we go to do the matrix multiplication, we're going to want to multiply the intercept term by 1. And then here in the second column, this is where we have our explanatory variable. So we can then represent the parameters in a 2 by 1 matrix, and it ends up, if we multiply this X matrix by this matrix of parameters, we end up with that matrix that we saw earlier. And so let's actually confirm that and see if that is true. So first of all, notice since X is an n by 2 and beta is a 2 by 1, using what we learned about matrix algebra previously, we know we can multiply these together because the inner two numbers match, and we know the resulting matrix will be an n by 1 matrix. Alright, so if we want to multiply the X matrix times the beta matrix, notice this is going to be equal to this matrix, which is the X matrix, multiplied by the matrix with the parameters. And so notice what's going to happen here. We have n different rows in our first matrix, and each of those n different rows we're going to multiply by this column here. So looking at our first element, we're going to have 1 times beta naught plus x1 times beta 1. And then when we multiply the parameter matrix by the second row of the X matrix, again, we're going to have 1 times beta naught plus x2 times beta 1. And we would keep on going all the way down to the nth row. And notice that gives us this matrix right here. So using what we just saw, we can write the simple linear regression model in matrix form. So we have that right here. Now typically the first way is how you're going to see it written, but you could also write it this way, and notice this way actually has the dimensions of each of the matrix next to it. But for convenience, the dimensions are usually left off. So it ends up there's some other matrix products that are useful, not just X beta. We could look at Y transpose Y, X transpose X, and X transpose Y. And so we're going to use these here in just a little bit. But one thing that you should notice in these matrices is if you go back to the week 2 notes, and if you'll recall, one of the things we did was we estimated those parameters by hand. So in other words, we had those formulas, we filled in the numbers, and we got our parameter estimates. Go back and look at those formulas, and remember we had that table that summarized everything, and at the bottom we had some different sums. Well, if you go back and look, you're going to notice that these matrices contain a lot of that information we needed to calculate those parameter estimates. So we've got the sum of the xi's, the sum of the xi squared, the sum of the yi squared, and the sum of the x times y. These are all pieces that we need to calculate those parameter estimates. Previously, in the last note set, we also learned about the inverse of a matrix. And it ends up the inverse of the X transpose X matrix is very helpful when it comes to simple linear regression or regression in general. So let's find the inverse of this matrix. So the first thing we're going to do is we're going to find the determinant. So recall that the determinant is equal to A times D minus BC, where those represent different elements in the square matrix. So looking at the square matrix that we have right here, that's going to be equal to N times the sum I equals 1 to N xi squared minus the sum I equals 1 to N xi quantity squared. Now, one thing that we could do is notice if I multiplied this term by n squared over n squared. So in other words, I'm really just multiplying it by 1. We can show that this is equal to n times the sum I equals 1 to n xi squared minus n times x bar squared. And you might say, well, why is that useful? Well, that can be shown if you go back and you look at the Module 2 notes. This is actually equal to n times sxx. So now we can find that inverse that we wanted to. So we have x transpose x inverse is equal to 1 over the determinant. Then we have, remember we're going to flip what's on the main diagonal. So we have the sum I equals 1 to n xi squared n, and then the off diagonal becomes negative. And again, notice we're starting to see some of those values that we saw when we calculated our parameter estimates by hand back in week 2. All right, so again, we can write our simple linear regression model as follows. And then the other thing to recall here is that the sum square of the deviation of the y values about the predicted values, or in other words, the sum squared of the residuals for all the n data points is as follows. And so remember that we saw in Module 2, this piece right here is actually equal to the residuals. And remember that we use the residuals to estimate the parameters epsilon, which are those true unknown errors that we can't actually observe. So it ends up that if we want to find those parameters estimates, what we're doing is we're finding the minimum, or the least squared estimates. And so we saw all of this back in week 2. So notice one thing that we could do is in this sum right here, when we define the SSE, we could replace that portion within the brackets with E and get this piece right here. So then writing in matrix form, it ends up that if you want to take the sum of something squared, that's the same thing as the column vector transposed times the column vector. And so we actually saw that up above. For example, if we look right here at y transpose y, which is a column vector transposed times itself. So, therefore, we could also write SSE as follows, because again, here we're looking at this in terms of the parameters. So I'm being a little bit cavalier here in terms of, which one's the parameter and which one's the estimate. But recall that the residual is equal to y minus x beta. And so that's where we're getting this piece from. And then you could use matrix algebra to show the following. So essentially what we're doing here is we're doing this multiplication. This multiplication can be a little bit trickier than regular multiplication, so I'm just giving you what that's equal to. And it ends up that the value of the beta coefficients which minimize SSE are the least squared estimates, and this results in the regression normal equations. So this is what's called the normal equation, and it's going to help us get our estimates. So notice here we have the x transpose x, we have the beta, and we have the x transpose y. Well, we just found the inverse. The reason that we need the inverse is, notice what we would like to do is get beta by itself here. Well, there is no division with matrices. Instead, recall that the inverse of a matrix times the matrix is equal to the identity matrix. So what we're going to do to get beta by itself is we're going to multiply both sides by x transpose x inverse. And if we do that, that makes this entire piece, because that's the inverse times the matrix, that is going to be the identity matrix, and we're just going to be left with beta. So this then gives us our estimates, which is beta hat is equal to x transpose x inverse, x transpose y, gives us beta hat naught, beta hat 1. And it ends up that if you do this multiplication, you're going to find the exact same formulas that we saw back in Module 2. And then we could do something similar to find our variance estimates for our parameters.